Hello, students. So today we're going to talk about inference with two population proportions. So I'm going to focus on the worksheet that's in front of you, but we will only get to a few of the problems because they're pretty in-depth. So I encourage you to look at the worksheet and answer the first two questions. I'm going to switch my screen so you can see my iPad and the work on that. But on the worksheet, try to answer the first two questions and then pause the video and go ahead and come back in when you've answered those. Okay, so when you're done answering those, for number one and number two, let's talk about them now. So for number one, the data was obtained. Whoops, I'm sorry, the wrong one. I'm on the wrong one. Here we go. The first one, you're trying to decide whether it's qualitative or quantitative. And we're looking at annual salaries. So we know that's quantitative. And because we're comparing the spouses, this is going to be dependent. Okay, because you're looking at spouses. The next one here, this is looking at the decision with two different groups. Okay, so we have a group that considers themselves to be religious and a group that does not consider themselves to be religious. So because those are two separate groups, that's the independence. And then you're just asking a question, is it morally acceptable or morally wrong? So therefore, that's qualitative. Okay, let's move on now. Number three, I'm going to look at number three. Researchers at Harris Interactive wondered if there was a difference between males and females in regard to some common annoyances. They asked a random sample of males and females the following question. Are you annoyed by people who repeatedly check their mobile phones while having an in-person conversation? Among 540 males surveyed, 178 responded yes. Among 560 females surveyed, 206 responded yes. Does the evidence suggest a higher proportion of females are annoyed by this behavior? Okay, so we need to answer some questions first. Explain why this study can be analyzed using the methods for conducting a hypothesis test regarding two independent proportions. Okay, so we need to recognize that the data was obtained by a random sample. The response variable is qualitative. Are you annoyed or not? There's two independent samples because you have a group of males and a group of females. Okay, so those requirements have been met. So now let's look at what are the null and alternative hypotheses. Okay, does the evidence suggest a higher proportion of females are annoyed? Does the evidence suggest higher proportion of females are annoyed by this behavior? Okay, so if I go back, if I write down the hypothesis, I'm going to first define what my symbols represent. So I'm going to say, let P of F be the proportion of females annoyed, and let P of M be the proportion of males annoyed. So we assume equality in the null hypothesis, and then we're trying to answer the question, is there evidence to say that females are annoyed more than males? So that's a right tail greater than test. Okay, so we need to get some sample statistics from the samples that were taken. We need to get our p-hat. We need to also check if we can use the normality requirement. So I'm going to go back to the worksheet and just make sure I'm following along with what you have in front of you. Okay, part C says verify the normal model may be used to determine the p-value for this hypothesis test. Okay, so this is what we're answering now. Okay, in order to do that, we need to look at the statistics. So from what's given, we calculate our sample, our point estimates for both the females and the males. And then we need to check, in order to use the normal model, we need to make sure that the sample size times the sample proportion is more than or equal to 10. So I'm just listing them here. I'm not doing the calculations just to save time because I'm trying to give you the concept of this. So we would actually calculate the sample size times the proportion of female who are annoyed times 1 minus the proportion of female who are annoyed. Make sure that's greater than 10. Do the same for male. And then we also need to check that the sample size is less than or equal to 5% of the population. Okay, so those I'll check. So we verify the requirements. And then the next question here is kind of squished on how, right here is part D actually. So it just printed kind of weird for me on this. Part D says, describe the sampling distribution of p hat female minus p hat male, and then draw a normal model with the area representing the p-value shaded for this hypothesis test. Okay, so we're looking at the sampling distribution of p hat female minus p hat male, and then draw the normal model with the area. Okay, so let's go back to my page here. So the sampling distribution of p hat female minus p hat male, we know it follows a normal model. It meets the requirements, so it follows this normal model. So it follows the normal model, has the mean of the population mean, and the standard deviation of, standard deviation is another formula. Okay, so let's look at how we find the mean of the difference in the proportions. We assume the proportions are equal. When we assume that the proportions are equal, therefore the difference is 0. So the mean of the difference is 0 because we assume the population proportions are the same. So the mean will be 0. And then the standard deviation is going to be this formula here. Okay, so in that formula, we're looking at the proportion of female times 1 minus the proportion of female over the sample size of each one, and then taking the square root of that. For hypothesis testing, we need to use a pooled proportion, which means we pool both of the successes of female and male and their sample sizes. We pool them together and we actually get this formula, not this. So we're going to use the pooled proportion, and the pooled proportion, like I said, comes from adding the successes, adding the sample size, so the number of successes over the number of sample size, and then calculating. That's my pooled proportion that I can insert into this formula. Okay, so for hypothesis testing, we need to use the pooled proportion. All right, so in my formula then, for the sample size, or for, not sample size, for the standard deviation. So my formula for the standard deviation, my pool value is 0.349. So 0.349 times 1 minus 0.349. I'm missing a parenthesis here. Times 1 over each of the sample sizes and the square roots of those. So if you calculate that, then we get the standard deviation to be 0.029. So the sampling distribution of the difference of the proportions of female and male, the sampling distribution follows a normal model with a mean of 0. And the standard deviation we just calculated to be 0.029. Okay, so if I have a mean and a standard deviation, and I know it's a normal model, I can draw a normal curve, identify 0 in the middle, and then add my standard deviations to the right and subtract them from the left to get my scale on the bottom. Okay, so I've drawn a diagram here. And in this diagram, here is my number line. I draw this normal curve. I put 0 in the middle for the mean. And then my scale, each of these marks is based off of adding 0.029 to get the scale to the right and subtracting 0.029 to get the scale to the left. Okay, so I draw the number line and I indicate the scale there. And then I know when I take my sample proportions and subtract them, I get a sample proportion of 0.038. I can mark that on my graph. So this is the location that 0.038 falls on my number line. It falls right there on my number line approximately. And then I'm going to shade the area to the right to represent the p-value. Shading the area to the right because we're looking at we're looking for evidence to say that the female proportion is greater than the male. So that's the area to the right. Okay, so I can find my p-value. I can use my calculator, and that we're going to be using StatCrunch as well. But because we're looking at proportions, that's a normal CDF. So we go to second vars, which is where you get that second vars, just to remind you that those are the 2 buttons that you push to get to the normal CDF. You enter in the lower of 0.038, the upper of infinity, and then the mean and the standard deviation from the distribution that we just identified. Okay, so we get a p-value of 0.0950. So that was the question we needed to answer for part D. We described the sampling distribution. We found that it was normal. We found the mean and the standard deviation. And then we drew the normal model with that area representing the p-value. Now we're going to look at the hypothesis test. Determine the p-value based on the model from part, and this should not say E, this should say part C. Okay, so I'm going to go back to my notes here. And we are looking at getting a test statistic. So our test statistic based off of the normal model, Z for proportion, it's always Z for a test statistic. For means, the test statistic is T, but for proportion, it's Z. And we can calculate it. And notice we also, again, have that pooled proportion in the denominator. And we already calculated that whole denominator here. We calculated that whole denominator when we looked at the standard deviation. So we've already done that here. Okay, that's that denominator right here. So I'm just going to put that value in 0.029, and then we subtract the sample proportions for each one, and we get approximately 1.31. Okay, so my Z distribution is a normal distribution with a mean of 0 and a standard deviation of 1. So I can draw my curve again. The distribution of Z-scores are normal with a mean of 0 and then a standard deviation of 1. Okay, so I'm going to erase some of this here. So my scale would look like 1, 2, 3, minus 1, minus 2, minus 3. So my test statistic from above, so there's my test statistic. 1.31 is right there on the number line. Area to the right represents my p-value. So again, I can use my calculator with the normal CDF. 1.31 is lower bound, infinity is upper bound, and the mean and the standard deviation for the Z-score, which is our test statistic. And look, we get the same similar value. It's off by a little bit. I think there's a little decimal error or decimal difference. And that has to do with how we rounded. So anytime you round here, we also, we rounded with the proportion. So because we rounded here and here, we get this proportion. So because of the round off error, there's a little bit of discrepancy in the p-values. Okay, so let's interpret this. We're going to interpret it by saying, okay, let's think of this as approximately 0.10. So that's 10 out of 100. So that means if the null hypothesis that we're assuming the proportions are equal, proportion of female is the same as the proportion of male. If the null hypothesis were true, we would expect about 10 samples in 100 to yield the same difference in the proportions. So that same difference of 0.038 or higher. In order to decide if we want to support or reject the null hypothesis, I need to go back to the worksheet because I think I'm getting ahead of myself here. So let's pick up. Okay, we interpreted the p-value. We just did that. And now we're on part G. Based on the p-value, what does the sample evidence suggest? That is, what is the conclusion of the hypothesis test? Assume 0.05 level of significance. Okay, so my level of significance is 0.05. Now there's my alpha level. So I'm looking at my p-value. I see my p-value is more than my alpha level. So with my hypothesis test, the right tail test, we do not reject the null hypothesis. There is not sufficient evidence to suggest the proportion of females who are annoyed is higher than the proportion of males. Okay, if you need to pause at any time, you can pause, you can rewind. I encourage you to do that as we go through these. Let's move on. So now we're going to number 4. Okay, so here again is where I encourage you to pause because there's a lot of terminology here and a great review for you to go back and answer these questions. So take a few minutes and try to answer these, pause the video, and then we'll go through these together. Notice part A starts up here. If you're looking at the screen, part A is actually squished up there, and then it goes to part B, etc. Okay, so after you pause the video, we can see that it is a completely randomized study. The response variable is whether the subject experiences dry mouth or not. It's qualitative, and there's 2 outcomes, dry mouth or not. The explanatory variable is the type of drug, and there's 2 levels, which is the Clarinex or the placebo. Double blind means neither the subject nor the person monitoring the subject knows which treatment is given, the Clarinex or the placebo. So neither one knows which treatment is given. Okay, and the importance of a placebo is because you want a baseline group to compare the Clarinex group to. And you also want to eliminate any effects due to psychosomatic behavior. So part F now is going to ask us to perform the test. So in order to perform a hypothesis test, we always need to check requirements. So for proportion, and we want to, if you're going to use symbols, especially subscripts, you really want to identify those. So I've defined them over here. P hat of C represents the proportion of the Clarinex with the dry mouth, and P hat sub P is the proportion, the sample proportion of the placebo group with dry mouth. So we can calculate those from the information given in the paragraph, and then we check the requirements for each of the samples. making sure those are both greater than 10. Those check out. We also check the sample size, comparing it to the population, 5% of the population. Okay, so all of those check, and now we can move into the normal model. So we are trying to test whether the side effects using Clarinex, the side effects of dry mouth using Clarinex is more than, I don't know why I have it up here, I meant to put a P, more than the placebo. Okay, it's a right tail test, and we're testing at a 5% level. So with the 5% level, we mark on our graph, this is a critical value of 1.645. And just as a reminder, if you want to find the critical value, you can use your inverse norm. Since this is a Z critical value, you can use inverse norm on the calculator, or you can use your stat crunch where you go to stat and calculators, and then you choose normal. And that's where you put in the area of 0.05 and you leave it blank for the value that separates the area to the right. Okay, so there's the critical value, critical region, and then you calculate your test statistic. So our test statistic, there's the formula for the test statistic. Again, we're using that pooled sample like I described before. So you would have to, so each of these up here are individual proportions, but to get the pooled sample, you would add both of the successes, the 50 and the 31, and then you would divide by the total sample size. So you would add the 1655 and the 1652, and that's your pooled proportion. Okay, so when you calculate that, you get a test statistic of 2.1292 approximately. And we can see, just if we compare that now to the graph, so let's put that on the graph. If this is 1.645, then 2.1292 is inside that critical region, and I've just now shaded the p-value area. Okay, so we can get that p-value, and we can get that with StatCrunch. I can take you into StatCrunch, which is what we're going to go into next, but under StatCrunch, you would go to stat, and then you would go to proportion stats. You would choose to sample, and then you would choose with summary, and you would be able to get the test statistic and the p-value in that way. I will take you in there, but I'm going to go through what's written here, so I'm not flipping back and forth at the moment. Okay, so we calculate the p-value with technology, and we get approximately 0.0166, which is smaller than my alpha level. Okay, we're testing at 5% alpha level. So since it's smaller then we do reject the null hypothesis. There is sufficient evidence to support the alternative, which is the claim that the proportion taking Clarinex experienced dry mouth more than the proportion taking the placebo. Okay, so let me go back to the questions, make sure I'm answering all the questions we have here. Okay, so we have completed part F. Does the sample evidence suggest the proportion of individuals experiencing dry mouth is greater for those taking Clarinex than those for taking the placebo at the 0.05 level of significance? Okay, so we just have completed that. Now we're on part G. Do you believe the difference between the groups is practically significant? Okay, so we said it was significant up here statistically. We said it was significant. We rejected the null hypothesis and said it was statistically significant. But is that practical significance? So take a moment to think about that. Pause the video, whatever you need. Okay, so let's think about practical significance. So if we look at the difference in the samples, so the difference between the Clarinex and the placebo, the sample portion there is approximately 0.011. Okay, and that came from calculating each of them and then I round a little bit more here. So I rounded to 3 decimal places here, if that looks different. So the difference is about 0.011. That's a pretty small difference. So it is not really reason to avoid Clarinex. It's statistically significant, partly because of the large sample size. So statistically, it came out to be significant, but really that's not much of a difference between the Clarinex and the placebo to make you avoid taking Clarinex. Okay, let's move on to number 5. Number 5, I think we're going to go through number 5 and then I will bring you into the technology. So let's go ahead and go into number 5 and then I'll be able to switch my screens here. Okay, this one is going to be a confidence interval. So we're going to look at confidence intervals now. So this has to do with the Iraq War. In March 2003, the Pew Research Group surveyed 1,508 adult Americans and asked, do you believe the United States made the right or wrong decision to use military force in Iraq? Of the 1,500 adult Americans surveyed, 1,086 stated the United States made the right decision. In August of 2010, the Pew Research Group asked the same question of 1,500 adult Americans and found that 618 believed the United States made the right decision. In the survey question, the choice right and wrong were randomly rotated. So why would that be? And the reason for that is to remove any potential non-sampling error due to the respondent hearing the words right or wrong first. Okay. So now moving on to part C, construct and interpret a 90% confidence interval for the difference between the two population proportions. So I know on part B, what I am trying to find is there's the difference. So that's my statistic, my sample, the difference p hat of 2003 and the proportion of 2010. So the difference between those two, adding and subtracting the error to get my confidence interval. The error is calculated with the critical value based on the confidence level. So that's how we find that critical value is based on the level of confidence. It's a 90% level of confidence. So we're going to look for the critical value of Z alpha over 2. So Z 10% over 2. So Z of 0.05, that critical value goes in the formula. And then notice here how we are not pooling the proportions. Here we keep the proportions separate. We're not using the pooled proportion because we're not assuming they're equal as we would if there was a hypothesis test. So we calculate each of the sample proportions based on the information given. So we get the proportion in 2003 and then the proportion in 2010. We calculate the difference. So subtracting those. So this difference is my statistic where I subtract error from it and then I add error to it to get my lower and upper bounds. Okay, so now I have a note here that I'm going to go into StatCrunch. Let me just write out what I said. So we are looking at taking this value, so the 0.3104, and we're going to subtract the error, and we'll take 0.3104, and we're going to add the error. So we're estimating the difference between 2003 and the proportion in 2010. So we're estimating the population proportion with these two lower and upper bounds. So the way we can do this is we can get into StatCrunch. We go into proportion stats, 2 samples with summary. It'll be the same place we do hypothesis testing, which is convenient. So when you do that, we get these results for the lower and the upper bounds. And we can interpret that because we just looked at a 90% confidence interval. We are 90% confident that the difference in proportions of adult Americans who believe U.S. made the right decision to use military force in Iraq from 2003 to 2010 is between 0.282 and 0.338. So there was quite a bit of a change, I would say, between 2003 and 2010. Okay, so let me go ahead and stop sharing my screen and let's go into StatCrunch. See if I can get us there. I need to open it up. Hang on. Go back. Stop sharing that. I need to open StatCrunch. Okay, so I think I need to open that. Stop share. Okay, I think I might do it. Let's see if I can get to it one more time here. Sorry. Okay. That's it. Okay, I think I'm there. All right, so you should see the StatCrunch on your screen. And then I'm going to go to Stat. And I'm just going to go ahead and do this, the one we just did. So the confidence interval, proportion stats. Make sure you can see what I'm seeing. Stat proportion stats. And then we go to to sample. And then we go with summary. Okay, so with summary, we can put in the number of successes. So we have to keep track of what sample 1 and sample 2 are. So I'm going to say sample 1 is 2003. So that's 1086. And then the number of observations was 1508. And then the number of successes for 2010 is 618. And the number of observations, 1508. Okay, so here's where we would choose hypothesis test, but we're doing a confidence interval here. And we want 90%. And that looks good. So let's go compute. And here's where we can get the output. So we can look at the lower and upper limit on the very far. So that's where I got those values there. Okay, so now let's go into, let's go back up to the ones that we just did. So let's look at number. So let's go back to number 3. So number 3 was the cell phone conversations with, are you annoyed by people repeatedly checking their mobile phones? So this was the females and the males perspective. So I'm going to look at part E. I got to get to the right screen here so I can get the information. Okay, I think I found it now. Okay, so we're looking at the proportion of female greater than the proportion of male. So again, I'm going to go to stat. I'm going to go to proportion stats. I'm going to go to to sample. This is with summary, so I don't have the raw data. So sample 1, I'm going to treat as females and sample 2 as males. So 2006, and the number of observations, 560. And then for number of successes for the males, 178. And the number of observations is 540. Okay, I'm going to do a hypothesis testing. So we're assuming they're equal. So P1 equals P2, which means that if they're equal, then the difference is 0. And then since we wrote proportion female greater than proportion male, then PF minus PM, PF minus P1, we're assuming that's greater than. So this will be a greater than sign, greater than 0, because the difference, if the female is more than the male, the difference between female minus male would be greater than 0. Let's go ahead and show the critical value. And my confidence level for this first one, let's see, what was it? 5%, I think. Yeah, 5% is what they asked us to. So that looks good. Okay, and then we're going to compute. And we get our test statistic, our critical value, and our p-value. Okay, so the test statistics, I had 1.31 by hand, but that was because I calculated some of this by hand. And that's also round off when you're rounding off proportions. both proportion of female and the proportion of male, and then you round it into the pooled proportion, that makes a difference in where you're getting round off errors. So the technology is going to give you the most accurate result. So this 1.33 instead of 1.31 that I had, that's why. Okay, the critical values based on your alpha level and whether you're having a right tail or left tail test, and then your p-value that you can interpret there. And I got p-value at 0.0951, so that also is just due to using my rounded off values. Okay, so there's that for the confidence interval. I mean, sorry, for the hypothesis test. Let's just do one more here. We want to go over number 4. So number 4 was when we looked at the Clarinex versus the placebo. So again, stat proportion 2 samples with summary. Statistics for this one is we had 50 for the Clarinex, and then 1655, and then for the placebo we had 31 out of the 1652. We're doing a hypothesis test, and we're looking, it's again a right tail test. So we're going to choose greater than. And critical value, this time we're testing at, again, 5% level, so I'm not changing that. Okay, and then I'm going to hit compute. And technology, there's your test statistic, your z-stat is your test statistic, your critical values based on your alpha level and whether you have right tail, left tail, or two tail. And then your p-value is the 0.0166 that you can interpret. Okay, so the last thing that I want to do is show you the calculator, and then I will send you on your way. So I want to share one more time. Not that one. Let's see, here we go. Okay, so I am back at the notes on my iPad. So on the calculator for each of these, so number 3, when we were looking at the cell phone one, so I'm just going to get a screen here. So with the TI-84, you have a button called Stat. So you can go to your Stat button, and then you arrow over to Tests. And this is a 2 proportion z-test. So this would be number 6, 2 prop z-test. Okay, so you want to select that one. And then it lists just like you would see in StatCrunch, X1, N1, X2, N2. You get to choose your tail on the test and you calculate. So that's how you can do the same things with your calculator. Sometimes I find it a lot easier to grab my calculator versus like trying to open up StatCrunch. The calculator is really effective for this, especially if you don't have data. So if you don't have data, I encourage you to use the calculator. If you have data, then of course StatCrunch is a lot more useful. Okay, well, that's it. I hope you have a great rest of your day. Bye.